Hello, absent students or someone coming back to the lesson for a review. We only have one, right? Yeah. Okay, cool. All right, so this will be for him. All right, so Jaron, you didn't miss anything. You're just, this is the first thing I've written, and hopefully this will help you learn this on your own. Okay, so here's what we're going to do. How do we get the direction vector? Well, it's a line. So the direction vector is the same between any 2 points. So if I've got 2 points here, I'm just going to take basically the final point. So we'll take 3, 2, 0 and subtract 1, negative 2, 4. So that gets us the vector 3 minus 1 or 2, 2 minus negative 2 or 4, and 0 minus 4, negative 4. So that's a direction vector for our line. Now, we don't actually have to use that vector. We can use any scalar multiple of that vector. I want to note that for us, okay? We can use any scalar multiple of this vector. Here's the analogous case for algebra 1. If you get a slope of 1/2, you don't have to use 1/2. You can use any unsimplified version of 1/2, okay? So that's kind of like, in this case, I could use 1, 2, negative 2. I could scale it down like that. So there's many, many different ways to write an equation of a line. All right, and then for a position vector, it's just any point on the line. So we've got 2 of them, so we can use either. I'm going to use the first one. I'm going to go with 1, negative 2, 4. Okay, so here is the vector way of writing the line. It's every point x, y, z on the line can be found by starting at the point 1, negative 2, 4, and adding scalar multiples of 2, 4, negative 4. So this expression right here, this equation, is one of infinitely many vector equations for the line. Because why are there infinitely many? Because there are infinitely many points that we could choose to start with. We could have chosen this one or any other point in the line. And there's infinitely many ways to express the direction vector because it's this or any scalar multiples of that. So that's vector form. Label that vector form. And then I want you to show you parametric form as well, because you'll see that sometimes, but it's really just that, almost identical. It's just x equals 1 plus 2t, y equals negative 4 plus 2t, and z equals 4 minus 4t. That's parametric form. Yeah?
Are we allowed to, like, instead of doing it in parametric form, just putting a bracket around 1 plus 2t, negative 2 plus 4t, and then treating it as a matrix?
Usually it's not written that way. I wouldn't say it's wrong, but that wouldn't be conventional. Joshua?
Why is the point in vector form represented in, like, as a vector, not like this regular form?
Think of it this way. Suppose that the origin is right here, okay? And my line is doing this. Here's what's going on. The point is the vector that takes us from the origin to the line. And then the vector is the thing that starts us there and pushes us along the line. That's kind of the visual for what we're doing.
But then wouldn't that be like, if this was the vector that took us from the origin to that point,
Yeah.
and the line was like this,
Yeah.
wouldn't that vector then be like from there to there and then from there to there all along that line?
That's correct. So the result of all these things are the vectors that point to the line from the origin. Yeah. So exactly, because if you take a what did I say? This was the line, right? So you've got a vector taking you to the line, and then you've got some sums of vectors. So you've got one here, one there, one there, one there, one there. All those new vectors, which are really points, right? This is why I loved showing you the video of Grant Sanderson talking about them as a point versus an arrow, right? They're really just points, even though we're kind of supposed to think of them as coming from the origin and going to the line. Okay. Yeah, let's actually show that. Can we draw that as a picture, please? So let's draw a little sketch of what's going on. So here's x, y, z. There's the origin. Let's suppose the line is doing this. That's our line L. So here is a vector that's a position vector. I'm going to label it P. It gets us to the line. And then I'm going to use, let's see, I'll use blue, a light blue, to show all the different scalar multiples of the direction vector. Right? So this is like V and KV and et cetera, right? So we're kind of going along the line like that. Well, all the points end up being, I'll do this in green. All the points along the line are the vectors that sort of take us directly to the line like that, right? Because the sum of P plus V or KV or whatever TV gets us to those points on the line. Does that make sense? Does that answer your question? Other people okay with that? So all you need is 2 points. With the 2 points, you can make a direction vector and then make your line equation. There's another form the textbook talks about called symmetric equations. I think it's pretty dumb, but if you just see it come up, I don't want you to be lost. So symmetric equations are like this when t is solved for. They're just like solve for t and equate all of the statements. So it'd be like this: x minus 1 over 2 equals y plus 2 over 4 equals z minus 4 over negative 4. This is a way of kind of eliminating the parameter, but still getting all the useful information. Because from this, you can tell that it goes through the point 1, negative 2, 4, and has direction vector 2, 4, negative 4, and you're not then concerned about this parameter t. However, it's problematic if one of these is 0, right? Like suppose z was always 4, then you'd have to leave this part off and just say, you'd have to write 2 equations. You'd have to say this, comma, z equals 4. So I don't love expressing lines in this form, but it is in the text, so you could see it come up. Okay, questions there? Okay, let's do a plane. Ready? Okay, let's just state the formula like you wanted it straight up, not derived. Some of you did, so that's what I'll do. All right, here's the plane. A times x minus x naught plus b times y minus y naught plus c times z minus z naught. You can either write it as plus d or, oh no, actually no, this is just equals 0. You don't need to have a d in that case. So there's the plane equation. So where do you get the a, b, and c? Just like in a line, where do you get the m and the b, in Algebra 1? So the a, b, and the c are called the normal vector. And it is orthogonal to the plane. That's kind of interesting, isn't it? That the numbers that appear as coefficients aren't actually vectors that lie in the plane. They're a vector that lies orthogonal to the plane. So the vector n, did you say y? Yeah. Well, I'm doing it this way to spare you the derivation. I'll show you the derivation soon. Okay, so ABC you can find by a variety of different methods. We'll see some examples in the text soon. Okay, and then x naught, y naught, z naught is just a point in the plane. Okay, so try an example for me, okay? I'll just let you guys do this by yourself instead of me walking you through the whole thing. All right, Memphis, Tennessee is calling me. So let's say, what is the equation of the plane that contains the points 2, 1, 1, 0, 4, 1, and negative 2, 1, 4. Well, let's give these letters. Let's call them P, Q, and R. So I'm going to pause the recording, and then I'd like you guys to try and solve that. And you can leave it in whatever form you want. There we go. Okay, we're back recording. Jaron, you only missed me staying. Well, what did he miss? You missed me speaking at a British accent, but it kind of comes and goes sometimes. I can't keep it going for a long time. Now, see, it still starts to fall apart. Okay, anyway. All right, so think of these 2 points as points in the plane. All right, we're going to now define a vector n, which I've mentioned already, as ABC. Okay, define that vector n as orthogonal to the plane. The vector r minus r naught lies in the plane, or maybe we could say parallel to the plane, right? It basically follows the direction of the plane. So r minus r naught lies in the plane. And if it's in the plane, therefore it's orthogonal to n. We've defined n as being orthogonal to the plane, okay? So r minus r naught lies in the plane. So we could say r minus r naught dotted with n equals 0. Because if you have something in the plane and you have the orthogonal vector, then those two will have a dot product of 0. Well, r minus r naught is just x minus x naught, y minus y naught, z minus z naught. I mean z naught. Did any of you watch Number File? Yes. Yeah, that's where you'll get some great British accents doing math. And then dotting with ABC, okay, equals 0. Well, you see it? That's basically the derivation. This was pretty short and quick, right? Dotting just means A times x minus x naught plus B times y minus y naught plus C times z minus z naught equals 0. And there's your equation of your plane. Now, can you write this in a different form? Of course. You can distribute and combine like terms, and it will look more like this. AX plus BY plus CZ plus D equals 0. Okay? Equivalent forms, right? They mean the same plane, get us the same information. The ABC is really the key information that we need. All right? This leaves us 25 minutes to do problems. I like that. Yeah. Sure. Now, there are 2 other things that I want to remind you of again. Hang on one sec. I want to remind you of, again, that we learned before. And I just want to state it one more time because you're going to see it come across in our homework. It's the distance between 2 planes, right? It was this, AX1 plus BY1. We derived this last class, I think. Or we derived its partner down a dimension, right? Over the square root of a squared plus b squared plus c squared. I want you to have this formula in your notes for today because it's going to come up in our work, okay? So this is the distance between a point and a plane, where the plane is written as ax plus by plus cz plus d equals 0. Now it's tempting to do for you every kind of example problem you'll see in the homework. But that kind of robs you of some of the chance to play with this a little bit. I know you might feel like I don't want to play with it, but I'm not going to do every kind of problem. But I'm also going to tell you that if you get frustrated with the homework, it's okay to give up after a little while. Okay, it's fine if you just can't handle it. And of course, I'll make the solutions. All right, but there's going to be some problems that expect you to kind of extend beyond just the examples I've done. I've given you the basics, and I'll have you try some of the harder stuff at home. Okay, so should I keep the recording going while we do the problems? What do you think, Jared? Yeah, that's true. That's true. What do you think, Jaron? Are you there? Okay, well, I'm going to keep the recording going, and just would you please promise me you won't be afraid to just make a dumb mistake?
Yeah, sure.
Do we trust each other enough yet? I don't know. Right. But you all don't have textbooks, do you? No. Okay. Okay. Let's do this then. I'm gonna copy and paste the problems from my PDF onto OneNote, and then we'll work from there. If you have a book, great, take it out. How do you find the vector from one point to another? Louder. You just subtract. Exactly. So you guys can take notes or not based on what what I ask. I'll post this, of course, online. Okay. So you just do final minus initial. That's going to be useful for finding a equation of a plane. Good. Okay, Ivan, you're up. Let's have you do. Let's have you do 11. So you're finding a vector perpendicular to a plane. You're almost right. Let's ask Keenan. Okay. Noah? There we go. So we need the cross product, cross P, of two vectors in the plane. This felt much less intimidating on Zoom than it does in person with 32 people. Yeah.
So, couldn't you also just take the coefficients of the equation of the plane, and you said that was the normal lines of the plane, right?
Yeah. Perfect. So that's a great statement. If you've got the equation of the plane, take the coefficients, and that's perpendicular to the plane. Well said. Okay, let's do one more from this bunch. And I'm going to give you a question that we haven't learned yet. All right, so this will be fun for the person who gets picked. 18. What are the traces of a surface? How do you find them? Amanda. Do you have a guess? The traces of, I have used the term actually, but I say a million things in a block, so. No? Okay, I'm going to ask two more people. Hamza. Oh, he's at the bathroom. Matt. No idea. Okay, the traces of a surface, we'll learn this next class, are when x equals 0, y equals 0, and z equals 0. So it's like, what happens when that surface, whatever it's doing in space, intersects with the planes, okay? So a trace is when x equals 0, y equals 0, and z equals 0, and they are curves, and they help us understand what the thing looks like. Yeah?
Is it like when you plug in 0 for x, y, and z, or just when x equals 0, and then y and z or whatever, and then y equals 0, and x and 0? Whatever.
Right, well, you said the second part, yeah. X equals 0, and then y and z are allowed to vary. Yeah, that's right. That's right. Okay, that's 3 questions from the concept check. Let's go ahead to the next part. I'm going to have us go to the true-false quiz. Now, I'm going to try and ask you to explain, but if you can't, that's fine. Okay, here we go. Let's do 3 problems from this set. Sufyan, let's have you do number 9.
Number 9, okay. For any vectors u and v in V3.
That just means R3, yeah.
Any scalar k, ku plus kv. Let's see here. Yeah, that's true.
It's true, you're right.
Yeah.
It's true.
Because if you, because what that's saying is, so the cross product would be just the area of the trapezoid, or not the trapezoid, the parallelogram. And what that's saying is...
Wait, let's pause him for a second. The cross product is only the area of the parallelogram when what happens? When we have magnitude, right? So,
Right.
But your reasoning, I think, is good still, that like scaling the whole area is going to be the same as if we scale one side and then cross product. So that one is true. Good. Okay, good. Thank you. All right, let's go with Mike. Can you please answer this one, number 4? For any vectors u and v, magnitude of u cross v equals magnitude of u times magnitude of v. That's false. Can you fix it to make it right?
You have to multiply by sine theta.
Good job. You would need sine theta. That's right. Good. And we'll do one more. Let's have number 6 answered by Josh. This one. Actually, my card was Sorkin, so that's not you. Where is Josh? Oh, back there. Okay. So number 6, please. Why can't I change my pen color? I'm really struggling here, okay? Let me close OneNote. You have a chance to think now. So is it that U cross V equals V cross U? True or false? What? False. What is the answer to that? How can we make it true? Gretchen? Yeah. One of them is just negative, right? U cross V is equal to the opposite of V cross U. Good job. Okay. Now let's do some problems, okay? So those are the concept. Now let's take some from the problem set. Okay. Here we go. Let's take number 6 and everybody read it. Okay. And Reva, tell me how to do it. You don't have to do all the work. I'll do all the work. Just tell me how to do it.
Okay, well, can I just convert it to the
Definitely.
vector from where it's 0, 1, and 2.
Good.
And then the other one would be 1, -2.
Perfect. So we want to find 2 unit vectors that are orthogonal to those. How do I get a vector orthogonal? Perfect. Let's start with that. Okay. So let's start with that. All right. So IJK. What was it? 0, 1, 2? Yeah. And then 1, -2, 3. Okay. I'm going to do it so that I can redeem myself Jaden's way. I, 0, 1, J, 1, -2. Okay. Now watch. Am I going to still make a mistake? It's this product that are the sums, right? Oh, crap. Didn't redeem myself. Okay. It's this product that is the positive sums. Okay. So it's 3i plus 2j, plus 0k. So we don't have to do that one. And then it's this way. That's the negative sums. Okay. So it's the j1 is gone. So it's will be minus -4i. So it's plus 4i and then minus k. So we have here 7 to -1. Did anybody do it on a calculator while I was doing all that? Or you did the other way. Wonderful. And you got the same answer? Okay. So Reva, can you make this a unit vector for me? Okay, let's do it. Square root of 49 plus 4 plus 1, which is root 54. Is that simplifiable? Who cares? Okay, so what do we do with that magnitude?
You would do 1 over 54.
Good job. So we're going to take 7 over root 54, 2 over root 54, and -1 over root 54. Now the question asked, find me 2 unit vectors. So what do I do? Plus or minus, yeah. I can just say that thing, that the original and its partner going the other way are both unit vectors that do that. Questions? Yep. If I use a scalar multiple, it's now that many units long. So if I put a 2 in front of that, it's now 2 units long. Okay? Yeah. Yep. Questions on this? Okay. Thanks, Reva. Good job. All right. Let's do 11. Oh, it's Jaron. Hey, buddy, come on, let's go. Okay, just kidding. It's Jacob. All right, Jacob, you're going to do 11, please. So it says, find a vector perpendicular to the plane through the points 1, 0, 0, 2, 0, -1, and 1, 4, 3. If you, and never mind, I'm going to let you take it away. Go ahead. Yep.
Like 101.
100 for A.
So it's A100. B20 negative. So B is 20. C is 143. Right.
Okay.
And then vector perpendicular to the plane.
Yep.
So she's saying that it's so we're orthogonal to the point to the plane that those points contain.
Yep.
So well,
Let him think. Let him think.
I mean, would you just use it would be like the thing we probably did earlier. So you just take two products, you make two vectors out of the point.
Okay, do it. Find me the vector AB.
Well, I'm just kind of stealing my notebook right now.
So what's the vector AB?
AB would be 1, 0, negative.
Good. Okay, so let's start with this. Let's say cross P of 1, 0, negative 1. Now find me another vector that lies in the plane.
The other vector would be AC, which would be 0, 4, 3.
Okay, so 0, 4, 3. Oh wait, let's use our new method. Control this, right? So 0, 4, 3. Good. Okay, so that is a vector orthogonal to the plane. We did it. So 4, negative 3, 4. We just use a cross product. So cross P and then two vectors. All right, now this is an interesting one. Find the area of triangle ABC.
I'm not really sure.
Okay, Chris. Oh, come on, you can do this. All right, do you know how to find a parallelogram area? Right. So let's find the magnitude of the thing we just found. Remember the calculator command? Norm. That's the area of the parallelogram. The triangle is just over 2, right? It's just half the parallelogram. So it would be root 41 over 2. So the thinking is 1/2 the magnitude of U cross V. Good? Yeah.
Could you go back to the vector?
Yeah.
Did you remember how you got the vector 1, 0, negative 1?
Yes. We subtracted B minus A. So 2 minus 1, and then 0 minus 0, and negative 1 minus 0.
Oh, I'm looking at 10.
Oh, sorry, yeah. Okay. Good? Okay, I like 3. I want somebody to talk me through 3. Okay, this is going to be Joe.
So, find U dot V, you could say the magnitude of U times the magnitude of V times cosine of our angle.
Good job. What's that going to be?
That's going to be 6 times root 2 over 2.
Well done. Okay, so we have 3 root 2 for the first part. Nicely done.
And then to find the magnitude of U cross V, you could do our magnitude of V times magnitude of U times sine theta.
Beautiful.
So it's going to be the same.
Same thing. Good job. Okay, now the interesting question is U cross V directed into the page or out of it?
U dot V is directed into the page. I'm really bad at this.
That's okay. Fingers in the direction of U. Curl toward V.
So I think
Out of the page. Good job. So it's out. Good. Wow. He gets applause, but no one else? Oh, all right. I was impressed that he knew cosine 45 in his head. That was very good. Nice job. Okay, let's do one more, and then I want to look at a problem I'm going to assign for homework so that you're not completely lost on it, okay? Let's do, I'm not satisfied with those. Let me find a different one.
You kind of all
Ooh, 21 looks fun. Well, I don't know. I think you'll be fine. Okay, here we go. This is going to go to Noah. All right, Noah, read it aloud for us. No, you're good. Intersects the plane, blah, blah. Okay. Now, this is what I mean by, I've taught you the basics. I think you can handle this question without me explicitly showing you an example. So do you have any ideas? Okay, so think about it. Let Noah think. Hang on. Thank you, Eric. Okay, let's do it. Watch. 2 times 2 minus t minus 1 plus 3t plus 4t equals 2. Substitution, right? Okay, so let's solve this. 4 minus 4t minus 1 minus 3t plus 4t equals 2. Did I make any mistakes? 4. Yeah, thank you. I did make a mistake. Okay, there we go. The t's combine to be negative 1t. Yes. And the numbers combine to be 3. So I've got negative t equals negative 1 or t equals 1. So how do I answer that question? Put 1 back in. So I'm dealing with the point 1 minus 1 or, 2 minus 1, which is 1. 1 plus 3, which is 4. And 4 times t, which is 4. So they intersect at the point 1, 4, 4. Okay, nice, good. Ooh, another applause. Okay, well done. All right, so let me just show you something that might be a little more challenging so that you, when you go home and you try to do this, you're not all upset. Okay. Could we take a look, please, at give me a sec. Okay. Let's look at 57 and 58. I can zoom in so y'all can see that better. Find parametric equations for the line of intersection of the planes, and B, find the angle between the planes. Okay. Shall I tell you how to do it or let you struggle at home? Yeah? Okay, I'm going to give you a hint. Just a hint, okay? All right. What do we need for a line? What two things do we need for a line? A position vector and a direction vector, right? We need a direction vector and we need a point. Okay. How are you going to find a point that lies on these two planes? Well, one, you could just do it by inspection, right? You could say, I don't know, I'm just going to come up with values that I think would work and see if they work in here. You could do that. Here's another hint. Let z be 0. Because if two lines, if two planes intersect, that means that they intersect in a line. So suppose these are my two planes, and the green marker is my line, right? It's where they intersect. That green marker is eventually going to hit the floor, right? And when it hits the floor, it won't go on a curve like that, but when it hits the floor, z is 0. So let's find the point when z is 0. And that's easy because you can let z be 0 and then solve the system, and you'll have a point. So that's how you can find a point. But how do you find the direction vector for the line of intersection? Any ideas?
Find 2 points.
What?
Find 2 points.
Find 2 points. Oh, smart. So you could find 2 points that lie on the line, or two points that lie on the two planes, and then use them to find it. That's a great idea. What would be another way? What was the main type of vector we learned about today with planes? A normal vector. What could you do with the two normal vectors here to find the line of intersection? See where what? Yeah, you're gone to something. I don't think you're quite saying it right, though. Okay, this thing has a normal vector, and this thing has a normal vector. Well, how is this vector related to both of those normal vectors? Orthogonal, right? So you could cross the two normal vectors, right? You could take 1, 1, 1 and cross it with 1, 2, 2. And that would get you. So we got a couple of ideas working here. And then, finally, how do you find the angle between the planes? Yeah, but with what vectors?
Well, you could find the one point that you have, and then just choose another
Yeah.
I can't remember how you do whatever. You find an angle between the two orthogonal vectors.
Good. Use the two normal vectors, right? This one's got a normal vector and this one's got a normal vector. Find the angle between those, then you have the angle between the planes. Okay? All right, so that's a little preview. We're done. I'll make up an assignment. I'll do solutions for you, but try and play with them a little on your own, okay? Thanks, everyone. Sorry, I can't hear you. Oh, I don't know.
Oh, yeah. It's